So, see how this first one says probably a student does not have long hair. So, S is the student has short hair. So the probability a student has short hair would just be P of S. Probability, short hair. Probability not short hair would have a line on top. The book, I think, uses a little line here, which looks more like calculus, but I use this to mean the opposite of, or just not. Are you guys with me? Mm-hmm. What symbols would I use for the probability of long hair?
L.
Probability of L. Well, what about probability of not having long hair?
L does.
Yeah, okay. If you want to use a little symbol, like, do we call this a prime symbol up here? If you want to use this symbol, because that's what the book does, feel free. Okay, you guys are ready with me roughly? So the very first problem, no math. They just want you to rewrite. And so further down they have and they have given, and they have ors and stuff. Okay. I don't think this book, so here's the probability of A and B, yes? If I remember correctly, I don't think this book uses that symbol there. Have you guys ever seen that symbol before? Some of you guys have? Well, yeah, I don't think that book uses, does it? It does? Neat. Okay, cool. So let me talk about that. It's a really good illustration of how I know shit. I just don't know what the book does. Okay. Let me erase. Oh, let's do it this way. All right. I'm going to review the formulas we did last time. I'm going to use the appropriate symbols in each form. Wouldn't that be nice?
Yeah, Joe. Use the appropriate symbols. Okay.
Jeez. So can somebody remind me the formula for the probability of A or B, which has this symbol? And one way to remember that symbol, I'm a parent, and you guys are my kids. And I'm like, you or you, somebody clean the room. You or you clean the, you is like, you or you, somebody clean the room. You, I make it a U shape, yes? That's one way to remember. It's also called the union. If I say A or B, I'm kind of like putting those two things together. So it's also called the union, and it looks like a freaking letter U. This is another way to remember it. So when I see that, it's or. Yep. Now the and is going to be nice. What's the formula for this again? So what's the formula for probably an A or B? Anybody remember? Or look it up in your notes real quick.
The probability of A plus probability of B minus probability of A and B.
And can somebody remind me why that's there? If I just add these two things together, what might I have done?
Oh, you count extra.
Yeah, I could have counted some things twice. And exactly what would I have counted twice? Anything that's in both A and B. That's why I got to subtract it off once. Okay, let me stop for a minute.
Can you give like an example of that?
We will.
Okay.
I just want to go over the formulas for the moment.
Okay.
Okay. What about the formula for probably an A given B?
It's the little line, right?
Good, it's a little line. It's not divided by.
Probability of A and B divided by probability of B.
I like it. We're semi-making a formula sheet here, by the way. Although you can't have the word given, so just put this in notes. Later we'll make the official formula sheet. Because just to remind you guys, or you remind me, and if you look at the board, you'll, well, have I put it up there? Yes, I did. What's happening a week from today?
Mini quiz.
The quiz. Damn it, Jeff, why don't you give us more warning? I did, it's on the homework sheet, so done since the beginning. We proved, well, I didn't really prove it, but we showed examples of where these formulas come from. We actually calculated probabilities before we even knew these formulas, yes? So how important are these formulas if I have everything I need to count? These formulas don't mean shit then, I don't need them. In fact, you could make mistakes if you try to use them, to be honest. So I'd rather just count. If I don't give you something to count, and they ask you probability questions, you have to use these formulas. Maybe. People don't trust me because you're not used to a math professor saying, oh yeah, sometimes you don't use a formula. But that's the reality. We did problems before we even knew these things. In fact, that's how we made these formulas, is we did it and then we went, what did we just do? Yeah? I love you guys. Okay. So the one, I think one we haven't talked about yet is and. I didn't give us a formula for and, did I?
No.
I sort of did. But let me do it this way. I'm going to give 2 examples of a situation with and. Right? In fact, I'll give 3. Because I'm feeling generous today. Have you guys ever been in a situation where you absolutely had to be up at a certain time? You're all students, so
Yep.
yes. Final exams coming. Has anyone ever done something to really make sure you're going to get up? And what have you done?
Set alarms.
How many alarms?
3.
3 alarms. Maybe even told your friend, can you call me? Maybe even whatever. Yes? You guys with me?
Sometimes it's
Some of you guys are just like, I didn't even go to sleep.
Yes.
Don't do that. All right.
Well, that's
I mean, it could work for you, but
No, it doesn't.
why would you set multiple alarms?
Because you have more of a chance to wake up.
Why?
Because you have multiple reminders, or there's multiple.
Yeah. So either one of them might not go off or something, or you have more of a chance to wake up because you're going to respond to at least one of them more likely. So if you only do one, you might incorporate, have you ever done this? Has there ever incorporated the alarm into your dream and then you sleep longer? I've done that. Holy shit. That's why I need the alarm. It's like, bang, bang. I'm like, I used to use music to try to wake up. And then I would just take that into my dream. And then half an hour later, I'm like, oh shit, that was a nice dream, but shit. Okay, let me stop. You guys kind of with me? All right, so in that same vein, real quick then, there's a probability that an alarm will not wake you up, correct?
Yes.
And that's why you do multiple. Same thing with the door. If you live in a really bad neighborhood, what's on your door?
Multiple locks.
Multiple locks. In fact, not just multiple locks, multiple different kinds of locks. Why?
Because probability is one of them stops and one of them.
Yes! Maybe this person knows how to undo 2 of them and can't undo the 3rd, right? So it's just a contingency plan, right? It's like, okay, if this one fails, I've got a backup. If that one fails, I've got a backup, yes?
Right.
So every time you add another lock, you are decreasing the probability somebody gets in, yes? Okay. Now, here's my, let's start with the sad example. What was it, 1986, I think? 1986. This is sort of, well,
The way you
You
started
guys-
that was hilarious.
it was 1986.
This is sad.
This is Joe would be like, no. So, you guys, space shuttle. You guys know the space shuttle?
Well, that,
Chopper.
or no.
Yeah, the one that blew. Well, unfortunately, if I talk about the space shuttle exploding, I have to be more specific about which time. Yes.
Yes.
So, young Jeff, I lived in Florida. So we would walk out and we could see the shuttle take off. Not like right there, but we could see it off in the distance. We could see a little speck of light going up. You with me? That day we didn't for some reason. And I still remember I'm in English class. I'm sitting 4th seat back from the doors right there because I like to get the shit out of there. I'm sitting and the announcement comes over. I remember it perfectly because being a little geek, I was all about that space shuttle. Oh my God. So when they came out with it exploded, they actually came over to the loudspeaker and the announcement said there's been a horrible accident, the space shuttle has exploded. Dude, that's like seared in my brain. You guys with me? I'm really sorry. But if you had any relatives or people that were on the space shuttle, I'm sorry to bring it back up. Okay. Does anyone know why it blew up? Yes.
Wasn't it like there was a panel on it that was like?
No, that's the second time.
Oh,
The second time is because one of the heat shields had come off, or enough of the heat shields had come off that when they came back in, heat got in and it blew up. So, yeah. First time, Want to see? Yes.
Was it a failure of an O-ring?
Yes. Oh my God, dude. All right. And what's an O-ring? Do you know?
O-ring is, if I remember correctly, it's helps to sort of seal fuel inside the boosters.
So an O-ring was like a valve to make sure that gas was going the correct direction. So why would you have multiple of those in a row?
Just in case one fails.
In case one fails. So if I have a pipe and I put my little O-rings in, let's say the probability that one of them fails, just to make it easy for us to calculate, it's much less than this. Let's say the probability that it fails is 1%. You with me? So I put multiple of them in case the first one fails. How often would the first one fail? 1% of the time. Yeah, let me write this better. Which is a huge ask for me. The probability that it fails is 1%. Okay. Now, so tell me this. What's the only way there could be an issue then if I have this pipe with 3 O-rings? What would have to happen?
3 of them fail.
All 3 of them would have to fail. So another way to say that is this one fails, and this one fails, and this one fails. So do you see how the formula for and cannot be the same as the formula for or? Because then I would be increasing the chance of it. 1% plus 1% plus 1% would be 3%. So why would we do that then if we're increasing the chance? So the formula for and cannot be the same as the formula for or. And more fundamentally, we wouldn't expect it to be, but just to point that out. Does everybody get the idea?
Yes.
I want to overall decrease the probability of failure. And that's why I put multiple things. Now, let me say it like this. How often would this one fail then? It's the same O-ring. How often would this one fail? 1% of the time. And this one fails 1% of those times. Let me say this again. This one would fail 1% of the time, correct?
Yes.
And 1% of those times, this one would also fail because this one fails 1% of any time. So what's 1% of 1%? Mathematically, what does of mean? Multiplication. And it makes me a little sad that people coming out of high school over the years have slowly not been told what the shit of means. Everybody used to know of means multiply. And now it's like, oh, is it divide? No. You guys kind of with me? Of means multiply. If I have half of 10, that's 1/2 times 10 is 5. Okay. So if I wanted to know what's the probability that the first one fails and the second one fails, I would multiply that shit together. Yes?
Yeah.
Okay. So what's probably the first 2 fail then? 1% of 1%, which is 0.01 times 0.01. How do you do that? Besides in your calculator. You write 0.1, and then how do you multiply by this? You move the decimal back twice, yes? So it's 0.0001. In fact, here's a really cool way to do this. I know you have calculators. I don't care. How many decimal places? 2. How many decimal places? 2. How many decimal places total then? 4. That's how you do that by hand. I know you have calculators. We're humans. We should know this shit. Okay. Did the probability go down matching with why we would put multiple O-rings? Yeah. So what if I had 3 O-rings in there? That's going to make that go down once, twice more. You guys kind of with me? So there's a 1 out of 100 chance one of them. There's a 1 out of, what is that? 10,000. 4 zeros after the 1. So if I do it one more time, if I have one more O-ring, it'd be 1 out of... Alright.
1 out of.
I'd add 2 more zeros. So real quick, I don't want to get too focused on this, but this is 1 out of 100, yes? Times 1 out of 100 is 1 out of 1, 1, 2, 3, 4, 1 out of 10,000. So if I do another 1 out of 100, I would add 2 more zeros here, which should push it over to 1 million. So overall, if I have 3 O-rings in my fuel pipe, there's a 1 out of 1 million chance that all 3 will fail. That's good. Now, real quick, what happened that day was it was really cold. The temperature affects the performance of O-rings. So all those probabilities of failure suddenly went way up. So it didn't matter that they had multiple in a row, they all had a higher chance to fail, and unfortunately, they all did. Yes?
Yes.
Okay, and then, yeah.
On the bottom, you put how much? Not out of 100. Can you explain that?
Sorry again? So
Um,
0.01 is 1 out of 100, yes?
Okay,
And then 0.01 is 1 out of 100, so when I multiply, I get 1 out of 10,000.
got it.
Which is just what that is, yes?
Got it.
How do I change from a decimal to a fraction? Well, how many decimal places? 4. So how many zeros do I put? 4. That's the shortcut for how to change from decimal to fraction. How important is everything I just talked about? Decimals are like not. Okay, just a quick little side note. Okay. How are we doing so far? Therefore, what operation does it make sense that and should end up having in it as a formula? Multiplication. Okay. Here's a silly example. All right. Let's say I want to join a group and they have kind of like an initiation thing I have to go through, right? And the initiation is simply this: I got to walk down this hallway, and every third step I take, somebody slaps me there, and every fifth step I take, somebody slaps me there. Yes, you guys with me? So as I walk, what's probably get hit on this cheek? 1 out of 3. Yes. What's probably get hit on this cheek? 1 out of 5. How often will I have this happen to me? Every third step, bam! Every fifth step, bam! Yes? How often will this happen to me? Don't make it do that again.
Not often.
Exactly how often? You could do it. You could do it. Yes! Every 3 feet. I'm sorry if you said it, I didn't hear. Every 3 feet I get slapped. Yes? Every 5 feet I get slapped. So every 15 feet. Yes? And isn't that 1/3 times 1/5? So how often will I get slapped on this cheek and this cheek involves multiplication again? Yes? Okay. Yes?
How would you write that?
Probability of L is 1 out of 3. L, Jeff, there you go. Probability of L is 1 out of 3. Probably R is 1 out of 5. Probably L and R is 1/3 times 1/5.
Okay.
Yeah. But that's my whole point with these examples is just to make sure you understand why multiplication being the operation makes sense.
Right.
Okay. If you scrutinize either of these examples too much, there's a little more detail I don't want to get into, so I just want them just to show you. So here's the ultimate way to figure out. So we know now that the formula should have times. It makes sense the formula will have times. Did and show up in any formula? It shows up in the OR formula, yes? But I have to know too much shit to be able to do that. So let's look at the given formula. Doesn't and show up in there? And real quick, why does it make sense that B is on the bottom? Because B is what I was given. So I know B happened, so my denominator should be based on B, because that's what happened. How do I algebraically solve this for what I want? Don't I want a formula for A and B probability? So if I just solve for it, I got it. How do I solve for probability of A and B? Multiply by probability of So I get probability of A and B equals probability of A given B times probability of B. So let me clean that up a little bit. And by the way, how do I want to say this? Yeah. I'm going to clean this up a little bit. Go ahead and write that down. What's probability of B given A? What's the formula for the probability of B given A? You can
It
do
would
it.
be probability of B and A over probability of A.
And if I multiply both sides by this, isn't B and A the same thing as A and B? Okay. If I multiply that up, I will get this formula. Do you see how they look different, but they both equal the same thing? So let me formalize this. Okay. So I wanted the examples to show you why it makes sense that multiplication should be involved. And sure enough, do we have multiplication involved?
Yeah.
Yes. Then I can come back to this and we can just do algebra to solve for the probability that I want, the probability of and. Yes? So now here's the official formula, and unfortunately for all of us, there's two ways it can be written. Probability of A and B is equal to the probability of A times the probability of B given A. Or it's the probability of B times the probability of A given B. Now I'm going to immediately do some concrete frickin' examples, yes? So all we did to get this was algebra. I just multiply to get the and by itself. That's it. The factors of the multiplication make sense now because of the silly things I did earlier. Yes? So now let's do a concrete freaking example. Dear God, Jeff. How many of you guys don't know cards at all? Like you don't know any of the cards in a deck of cards.
Oh, I say cars.
Oh, cars. Yeah, cars, I would show off my complete ignorance. The only things I know about cars are when my first car started having shit break down, I would learn about it. And now, you know, everything broke down to that damn thing, so you think I knew everything about it.
Yep.
Cards. Cards. Playing cards, yes? Give me a card that's in a deck of cards.
Queen of Hearts.
3 of hearts. Give me one that doesn't have a number on it.
Queen of Hearts.
Queen of hearts. Right? Jack of diamonds. Ace of spades. You guys kind of with me? That's all I
Queen
mean.
of Clubs.
No, some of you guys are like, no, Jeff. Okay, let me think if I can. Let me come up with a different example. Yes. Yeah, this was me talking about stuff, so this is the better page to put down. Yeah, this is a clean, this is what the formulas are. Okay, let me see. Okay, I want to give an example that's different from some on a worksheet that we have later. Let's say I've got. Let me see. Okay, let's say I've got 20 cars in a parking lot. Yes, 10 of them are Toyotas. 6 of them are Hondas. And 4 of them are what do you got, Jeff? BMWs. Oh yeah. Okay. Sorry if you're not represented. Now let's just do a quick. If I pick one car, what's probably I picked a Toyota.
10 out of 20.
10 out of 20. Easy peasy. Yes, easy peasy. So here's where things get different. Okay, so ready with me? Yep. What's the probability? What if I pick 2 cars? I'm gonna pick 2 cars. Yes? So I've got people in a parking lot, they all wanna leave. And somehow I am king of the parking lot, and I'm like, I will tell you when you can leave. So I pick 2 cars. Yes? There's 2 ways I could do that. I could pick a car and let it leave, and then pick another car. You with me? Or I could pick a car, change my mind, and then pick another car. So nobody leaves in between. Does that make sense? So like if I pick a candy bar out of a bag, could I pick one, eat it, and then pick another one?
Yeah.
Wouldn't that change the number for the second probability? Wouldn't the number of candy bars in the bag be different?
Yeah.
But if I pick one and go, I don't want that.
It doesn't
There we go. Then between the 2 picks, this number would stay the same. Does that make sense?
Right.
So I could either do it with replacement, or I could do it without replacement. Yes?
Yes.
Okay. I love you guys so much. Let me do this again. Does that make sense? So again, I could pick a car and let them leave. That would be without replacement, because I would let them go, I wouldn't put them back. Or I could pick a car and go, yeah, come on. Nah, go ahead. You, come on. So that would be with replacement, yes?
Yes.
I love it, guys. Say again?
From the first chapter,
Replacement. I don't think replacement like this has come up yet. I could be wrong. I don't think this idea of replacement has come up yet. Chapter 1. Maybe they did talk about that. Huh? Maybe. Because that becomes an issue later about how we pick a sample and if we might be able to pick a person twice. Okay, they might have discussed it there, but I know I didn't talk about it yet. Yeah, with replacement means I pick somebody and then I put them back before I pick somebody else. So I could pick that same person again. Does it make sense? Okay. I love you guys. So I'm blindfolded in this parking lot, and I randomly pick a car and I look at it. I'm like, no, and then they move around and I randomly pick a car. I could get the same car again, couldn't I?
Yeah.
Okay, good. But if I go, yeah, you leave, and then I put my blindfold on, can I pick that same car again? No, because it's gone. Okay, that's with replacement was the first, without replacement was the second. So if I do this, if I pick 2 cars, I have to tell you how I'm doing it. So let's do it with replacement first. What's the probability that I get a Toyota and then a BMW? So I want this to make nothing but sense. So this is me, I pick somebody and I point at them and I take them and they get excited and then I'm like, no, not you. You with me? I have no idea why this situation is happening, but it just is. Yes?
So it would be 10 out of 20 still because it has replacement, and then the BMW would be 4 out of 20.
And what do you do with those 2?
You would multiply.
Because it's and. So it'll be, what's the probability I get a Toyota?
10 out of 20.
10 out of 20. I look at it and go, you look, stay. And then I pick somebody else. Do you guys see what I'm saying? So if it's or, what's the operation? Or, if you look at the formula for or, what's the operation? Basically, no, or.
Oh,
I love you guys so much. Look at the formula. Or is basically add. Or is basically add. And is basically multiply. I love it. Do it again? Oh, okay. I love you. So of is a more basic idea. Of means multiply. When I say half of something or 7 of those, right? If I had, every box had 2 apples in it and I have 7 of them, that's 7 times 2. So of is a very, very basic idea. In terms of probability, figuring out an and involves multiplication. Figuring out an or involves addition. So, the way I look at this kind of problem is I look at it like a hangman game. You guys ever played hangman?
Yeah.
You guys know what that is?
Yeah.
And of course, we used to play it back in the day before we had like computers and shit. We'd sit around, we'd play Etch-a-Sketch and hangman all day. That's all we had. It was so the probability I get a Toyota is still 10 out of 20. You guys with me?
Yeah.
Right.
Then I put that back. So how many cars are there still in the lot? 20. And then what's the probability I get a BMW? 4. Now if you multiply those together,
40 over 400.
not 100, no. 40 out of 4, oh I'm sorry, did you 400? Okay. 40 out of 400, yes? Or half of 4 20s is 2 20s is 1/10 is 10%. Let me stop. Is everybody with me? So when you see an and question, and by the way, didn't we do an and question when we had the contingency table?
Yeah.
Didn't we do some and questions? Did we do this shit at all? Why didn't I have to do this shit? Because I can count everything I needed, yes? I had it all filled in, I could see the intersections. Here, I don't have a table of everything that could happen if I pick 2 cars. I've gotta use the formula. I'm trying to get you guys to understand. This is so weird to hear a math teacher say. but do not always use the formula. If I have all the numbers just sitting there staring me in the face, I just calculate the probability. I can just look at it, right? And as an intersection, I can make it. If you try to use a formula, it's going to make it much worse. It would work, but you probably won't do it right. And not because we're bad at it, but because it's harder. Okay, love it. So, same situation. Everybody's got this written down, yes? Same situation, but now I want to pick without replacement. Replacement. So I don't let the car leave. I put the car back. Yes?
Right.
So now I want to know what's probably the Toyota and then a BMW.
So the first one would be 20, right? Because that's your first pick. And
I haven't done anything yet when I pick the Toyota, right? So what's the probability that I pick a Toyota first?
10 out of 20.
10 out of 20. And then I let them leave. So what changes now?
The denominator.
The denominator.
The denominator changes, yes?
Yeah.
Yeah.
Because now how many cars are there to pick from for the second time?
19.
There's 19. Not 10.
Because you only picked one.
This is 10 chances out of 20 to pick a Toyota. That's why the probability is the way it is. But how many cars have I picked here?
One.
1. So how many cars are left? 19. I want to make a big deal out of that because that happens a lot. That's the most common mistake is people put 10 out of 20 and then something out of 10. I didn't pick 10 cars. This is the probability that I pick the 1 car.
Yes.
Say again? Okay. What's physically happening here? I pick a Toyota, I blindfold myself, I point to somebody, and then I say leave. And then I blindfold myself again. I'm about to pick the second one. How many cars are in the lot now? 19. So what's the probably going to BMW? It's going to be something out of 19 because there's 19 cars. So what's probably going to be BMW now?
4 out of
4.
19.
4 out of 19 because there's still 4 BMWs.
Yeah.
And then whatever the shit that is. 2 out of 19 would be a little more than 10, so like 10.7%.
I think it's 10.5.
I,
10.53%.
ooh, look at that. You win. 10 point who?
5.3.
5.3.
Should you always round up? So
What did I say? As a decimal, I needed to have 4 decimal places. So when you make it a percentage, it should have 2 decimal places.
Okay.
Yeah. All right. Okay, let's do some more. What if I do this? Pick 3 cars without replacement. Let's probably get a Hyundai, and then a Toyota, and then a Hyundai. What's the probability of? You guys with me? Does that question make? I'm gonna pick 3 cars. I want the first car I pick to be a Hyundai, or what is it? Honda? Okay. I forgot what I even said. It's a Honda. First car I pick is a Honda. I let them go. Next car I pick is a Toyota. Let them go. Next car I pick is a Honda again. Let them go. You guys with me?
right.
So how many spots am I gonna have? How many empty spots am I gonna have? You can do it. How many things am I doing? 3. 1, 2, 3, and I'm putting times between them because what does and mean? Times. I'm gonna multiply, yes. Or is add, and is multiply, yes.
So question for you. So you already picked a Honda, right? So that means
No, I haven't written anything, so I haven't picked anything yet.
Okay.
When I start writing, that means I've picked something.
Right, but when you do, so right, so like it's 6 out of 20 because you have 6.
All right, so let's start.
Okay.
What's the probability that the first car is a Honda?
6 out of 20.
And I let them leave, yes?
Right.
How many cars are left?
19.
How many Hondas are left?
10. Oh, 5.
You guys with me?
Right.
How many Toyotas are still there? So how many cars are there?
19.
And how many Toyotas are there?
10.
There's still all 10 Toyotas, right?
Yeah.
I haven't picked a Toyota yet, so there's still 10 of those. So that's Honda, that's Toyota. Now I want another Honda. How many cars are in the lot now? 18. How many Hondas are there? 5. So real quick, is this the probability I pick a Toyota? Is this, in fact, just go back. What was the probability that we pick a Toyota? Very first thing we did.
10 out of 20.
10 out of 20. So is this the probability I pick a Toyota? No. This is the probability I give to pick a Toyota, given that I already picked a Honda. Do you see how each of these probabilities are given that we just did this thing?
Yeah.
So now if you look back at the official formula for and, do you see how it's something times the given? So the probability of Toyota times the probability of Honda, given that I already picked a Toyota. That's why the numbers do what they do. But even here, did we really use the formula, or did I just go and show you how what we're doing is the formula? We did not, you guys did not use the formula, did you? Why didn't we have to use the formula? I gave you everything you need to count. But I wanted to point out, everything we're doing is exactly what the formula would want me to do. But we didn't use it because we're just doing what makes sense. And whatever the shit that, I have no idea. So let's see, 1.5, 3/20 is like, 5 18ths is like, nobody's gonna say 1/3, so 0.05, a little less than 0.047, what is it?
0.27777.
Is it?
Yeah.
All of that?
Well,
I
okay.
really did it wrong in my head.
If you did 5 over 18, but if you did it all together, it's 300 over 6,840, right?
Which is what? What did I say? Darn it.
0.04.
Ah, good, that's what I said. All right, I feel pretty good. All right, sorry. If you multiply all this shit together, yes? And please, dear God, try to do that right now. If you need to borrow a calculator, you can. Let me know if you have any issues getting this answer. In fact, let's do it here. You're going to need a calculator here later today, so just throwing that out there. 6/20 times 10, thank you, 19ths times 5 18ths. So you can put it in just like this, yes? Cool, thank you. Cool. Yes.
So when you found out, because it's 438.
So it's going to be 0.0439.
So you do the fourth.
Yeah, what do you always do for probabilities? As a decimal? 4 places, yes? So it'll be 0.0439. Don't chop round. Yes?
Got it.
Does it make sense? So 0.0439. Which I think is what I said. I'm sorry, I just am really excited when I get to show off that I know math stuff. This is my one skill. Okay. I guess feel. Does this make concrete sense to some degree?
Yep.
Because you could track. We're not using the formula, but it's exactly what the formula would have wanted us to do. And we're like, yeah, we got your formula. We don't need your shit. We're humans. We know what we're doing. So what if I had picked 7 cars? There would have just been a string of 7 freaking little fractions, right? I would make each fraction. I put it all in my calculator. You guys see? So this is easily scalable. Yes? Let me stop for a minute. Okay. So. By the way, what is 6 divided by 20? 0.3. What is 5 divided by 18? 0.277, yes? Yes? Now, are these two like really different? No. Are these two substantially different from the standpoint of probability? 30% chance of something is different from a 27.7%. If I was going to surgery, I'd rather have a 30% chance of it going well than a 27.7% chance. So it is practically significant. Yes? Because I'm not picking a lot. Once I picked a couple cars, aren't these both the probability I'd get a Honda in some situation? You guys with me? Didn't it change by a decent amount, the probabilities? Okay. This is gonna getting into the next thing I'm gonna talk about. I didn't need to know any of this shit to do the problem, yes? Okay. So why does it change so much? Well, how big was our sample?
20.
Yeah, there were 20 cars to pick from, yes? So the minute I changed the denominator by one car, all the probabilities changed by a decent amount. They changed by quite a bit. You guys with me? What if I had had 48 billion cars in this lot? Yes?
Right.
And I let one leave. Do all the probabilities change by a large amount?
No.
Yeah, because it's,
All right, come on now, you can do it.
yeah.
So let's say I have 1 billion cars in the lot, and 10 of, all right, let's not make it 1 billion. Let's make it 1 million. I have 1 million cars, yes? And there's 10 Hondas, yes? If I change the denominator by 1, this 10 out of 1 million different from 10 out of 999,999?
Right.
Are they very different? 10 divided by 1 million versus 10 divided by 999,999.
Yeah.
Is that very different? You guys can do it. You guys
It's
can do it.
one place. So
Let's try it. Let's try it. Let's try it. What is 10 divided by 1? 0, 0, 0, 0, 0, 0. A million is 6 zeros. Yes, 10 divided by a million. You can't even do it. Right? It's 0.000. Let's write it down. 10 divided by a million would be 0.12345 So move the decimal back 6 times, so 5 zeros. You guys with me? Now, what is 10 divided by 999,999? That is 0.000001000001. Would you say those are very different?
Yes. No. Yes.
Isn't this one this?
Um.
Isn't
Right.
right? Are those very different? Hell no. In fact, if I said, is 1.7003 very different from 1.7002? You would say no, yes? Do you see how that's different in like the 6th decimal, not even the 6th, the 12th decimal place, whatever the shit, yes? Okay. So when I have a very large population that I'm picking a few things from, the probabilities won't change, barely at all. So, when I have a very small population, I do it exactly like this. I track how the probabilities change. Yes? If I have a very large population, so let's say I pick 3 people from the US, right? And I know the probability that somebody's left-handed is 11%, yes? You guys with me? Every time I check, it's still about 11% is the estimate for the percentage of left-handed people. How many people in here are left-handed? I think I already asked you, right? 1, 2. Who said 3? Somebody said. Okay. So I can do 3 out of, there's about probably 20 something of us in here. So we're kind of close to 1%. You guys gonna, if I pick 3 people, and I wanna know what's the,
What does that say again? Like from the US
oh yeah. And we know
okay.
the probably left-handed person's bone. I wanna know if I pick 3 people, what's the probability to get a left-handed person and then not left-handed and not left-handed? Of course, why don't I just put right-handed? Because some people are both-handed and some people don't have both hands. So I need to put, is this fun? This is doing over here. I need to put not left-handed to indicate you're not left-handed because there's a lot of other things you could be besides left-handed. You guys,
Okay.
I would give my right arm to be ambidextrous. Isn't this the same question, the Toyota, the Honda Toyota? Doesn't this look the same?
Right.
It's totally the same. How big is our population?
I have no.
The population of the US.
Do you guys know roughly how big the population of America is at the moment?
400 million?
I think it's about 350 million.
That's it.
I think it's 380.
That's it.
Isn't there like billions of people? I feel like America's so big.
The world's got like 8 or 9 billion people.
Yeah, we're
But
actually
America-
smallest.
Oh, poor bit of one.
Majority of population China and India.
Yes, exactly. Okay, you guys can fact check me, but it's under 400 million. Pretty sure it's around 350, 360 million at the moment. I still remember when we passed 300 million. Right, but I'm not old enough to be saying, you remember there's 2,000 people. Shut up. I'm not quite that old yet. So, here's my point. Let's see if you guys really get this. I do not have to make a stupid little fraction out of this. Because if I take 1 away from 360 million, does that change my probabilities that much? No. So, when I have a really large population, I could just use the same probability over and over. So, the mistake people make all the time. Here's a mistake. Don't even write this. Here's a mistake. What's probably left-handed person? They say 11 out of 100. Then they go not left-handed would be 89 out of 99. And then they go 88 out of 98. What are they assuming?
That you're not.
How many people are in America?
100.
100. Okay, that's obviously not good. Yes. So if my population is very large, I can just do this. You ready? Let's probably pick a left-handed person.
11%.
Let's probably pick a not left-handed person. You can do it. If that's 11%, what's not left-handed? What must be true? If the probability it's going to rain today is 5%, what's the probability it's not going to rain?
Maybe
80.
Just answer that question. The question right now is about rain.
95%.
Don't come at me with them because I'm worried.
95.
Probably it's going to rain today is 5%, probably it's not going to rain is.
95.
So what must be true about any two opposite situations? The probabilities have to add to be
100.
100% or 1, yes? So probably left-handed is 11%.
91.
Probably not left-handed is 89. And so what do I put here?
89.
89, good. Because our population is so large, I'm not going to do the denominator bullshit. The probabilities basically stay the same. Maybe now it's like 0.88, a billion nines and then 3, but that basically is freaking 0.89. All right, I'm hoping you guys get this. So when I have a very small sample, I have 30 chips in a bag and 4 of them are green. Then you have to make ratios because every time I take a chip, the probability changes by a decent amount. You with me? If I'm talking about picking somebody at random from China, I don't have to make ratios. You don't have to Google the population of China to do that problem.
Oh,
Yes?
so just take
You just leave the probabilities as they are for each thing. Maybe. And then whatever the shit that is. Don't say it. Let me try and do it. 0.81, 0.08, so that would be roughly, it's a little less of 0.078.
It's 0.071.
Okay.
That's crazy.
No, I have to retire. That's a lot off. I feel bad. 071,
No, 0.0871.
0871?
Yeah.
Okay. Now I feel really bad. I was really off.
No, I think you were really right on it.
Okay. Thank you. I appreciate it.
Yeah.
Okay. So I think we're ready. I'm going to give you this handout. You don't believe it? I have a handout. Did I bring them with me? That would be neat. Yes. Andy.
If it doesn't say with replacement or without replacement, do you just automatically assume, because like in this thing it is 3 people, that would be without replacement?
If it doesn't say, you have to, well, I think it says it every time, and I'm gonna be very careful to say it. Because to be honest, there's no real, you'd have to assume it's without replacement, because
You're
physically
picking-
that's what we would do most of the time.
Right.
If I'm gonna pick 3 people, I need 3 people to come with me. If I pick you and then put you back down, couldn't I pick you again?
Yeah.
And couldn't I pick you again?
Yeah.
Did I end up with 3 people? No. So in reality, when we pick things, we normally pick it without replacement, yes. But I'm pretty sure they're pretty good, and so will I be about telling you exactly which situation you're in. So on this sheet, one side says, this side in class.
Oh.
So that's the side we're gonna do. The other side is a practice quiz, just like a practice test. Because a week from today is the double quiz on probability, yes?
Yep.
So next time I will have an answer for you for this. I think I'll even make it computer generated so you get a break from my handwriting, which is always nice. So the side that says this side in class, I want you guys to work on. If you want to work with other people near you, feel free. I'm not going to force you into groups. If you don't trust these people, just work by yourself. And you can have all your formulas sitting there, but the first problem you definitely don't need formulas for. Yes. If you still need to borrow a calculator, come on up here and do that. Some of you guys are quickly approaching your limit of working on this. Let's see. Oh, I got one. Okay, let's see. So the first thing when I give you this kind of problem is to add everything up. So double check me as I go. Is that right?
Yeah.
Thank you, guys. And then this would be 147, 164.
Yep.
And that'll be 56.
Yes.
Dudular. And then I get 220. That one I cheated because I remember what you guys got. Okay. Let's finish. Not a single problem in this question do I need to use a formula for. Can I? Of course, because they must always work. Yeah? But I don't need to because I have all the counts. I can just get all the counts. So what is the basic idea of probability? On the bottom goes everybody it could be. So what is the one problem A through E where the bottom won't be 220? E. Because E is the only one that I give you information so you can ignore everybody else. Every single one I have no idea, so it could be any of the 220. Okay. Out of the 220 for part A, how many match what I'm looking for? 164. So a lot of you guys said 85, understandably, because your brain says, well, 85 is right next to the word gross one. Yeah? So what the shit do you want from me? But the whole first row is gross one, yeah? So you got to go to the end. That's why the first thing you do is tally up every row and column. So this one should be 164 out of 220. I want to give myself some room. What is that as a decimal? 7455.
Yes.
There we go. 436. Okay. If you want to write it as a percentage, it would be 74.55%. If you want to, you don't have to. Now we reset, right? B is its own question. Business majors. How many people am I talking about total? That I could have picked, 220. Out of those, how many match what I'm looking for? 122. What's 122 divided by 220? Who is it? 55555? 555? 55. I get 5545. Is that what you're saying? 5545. Okay. Sorry, guys. Yeah, Jeff, as we were saying.
I forgot to add.
Now, OR is basically add, and is basically multiply, but I'm not going to necessarily do that. OR always makes things bigger, because there's more chances to get in. So one way I was explaining it to somebody was, I'm trying to make a group of people that match what I'm looking for. What's got to be true about the people who get into my group on part C? They could either be computer science majors, or they could be gross one students, and that's why my group should get bigger than it would have been otherwise, because I'm like, you can do either thing, I don't care. So, I'm going to show you two different ways to think about this. I could think about it more like the formula, and I could do 164 gross one students, plus 73 computer science majors, but what have I done?
Added two.
I added
62 twice.
62 twice, so I gotta subtract 62. Now, here's the other way to think about this, because I have all the counts. If I add 164 Grossmont students,
And then just add
how many computer science majors have I not counted yet?
11.
11. And of course, what's 73 minus 62?
175.
73 minus 62.
It's
73 minus 62.
11.
11. So I could just start here and say 164 Grossmont students plus 11 computer science people I haven't counted yet. So if I just don't double count them in the first place, I don't have to subtract shit, yes? So I don't care which way you do it, mathematically, it comes out the same. And of course, Jeff's scribble is different, but. So you get 175 out of 220, yes? And then whatever the hell that is. 0.095? That sounds too small. Should be
It's
way more than,
79.55%.
Yeah.
yeah. Yeah. Oh, this might be what you're saying, but you put an extra zero in there maybe, so 0.7955? Is that cool? 0.7955? There's a lot of 5454s there. 7, 9, what'd I say, 5, 5. Yes.
Right. So the equals, you put 64. Is that F? Hello?
Plus, that's
Oh,
why I
oh,
rewrote
oh,
it up
sorry,
here.
okay.
You're, no, don't
I just wanted to
apologize to
make
me
sure-
in my
wanted to make
horrible
sure.
way. So the top is always the total number that match what I'm looking for. And the bottom is always the total number of people or things it could have been. Every single problem we've done so far has matched that idea. And we'll continue. So part D, I'm gonna do it both ways. I am. I'm gonna do it the way you should do it, and I'm gonna do it the really silly way, okay? Just to show you I get the same answer both ways. The way you should do it, because I have all the counts, the top is always the number of things that match what I'm looking for. Well, how many students are math majors and Cuyamaca students? Only 8 are both, yes?
Yeah.
Out of how many total students it could have been?
22. 220.
220, of course. Because I don't know shit about the students, so who could it have been any of the 220 students? If I picked a student and said, oh yeah, by the way, they go to Cuyamaca, how many people could it have been? 56, yes? If I pick a student and I say, oh yeah, they go to Cuyamaca, how many people could I have picked? 56. The bottom would have become 56 if I would have given you that information. I didn't give you shit. And you're all like, yeah, do you see what I'm saying? Who could it have been that I picked? Any of the 220 people. How many match what I'm looking for out of those? 8. Now, real quick. Dear God, don't even write this shit. Don't even write this shit. But I want to show you. I want to show you it'll still work. Is everybody with me? What is 8 divided by 220? I almost don't care.
0.0364.
70, okay, good, beautiful, sweet. Obviously I do care because that's your answer. So I look at it as this is your work, this is your answer. So if you just put decimals out of nowhere, you will lose points because you didn't show me work. If you get it wrong, you'll lose the most points because you didn't show me work. Does that make sense? Okay, so I'm gonna do this one a very, very silly way. In fact, let me get a clean piece of paper. Math major and Cuyamaca student. Right? This would be the probability of a math major times the probability of a Cuyamaca student given math major. Yes? Just watch. Don't even write this shit, okay? That's the formula for and. That's one formula for and. Is that cool? What is the probability that I pick a math major?
25.
No, what's the probability I pick a math major?
25.
25 out of
220.
220. Now, what's the probability they're a Cuyamaca student given their math major? So what would go on the bottom then if I'm given that they're a math major?
56.
Given that they're a math major, 25, yes? I could only be talking about 25 students on the second probability, yes? Out of those 25 students, how many are Cuyamaca students? 8. What do the 25s do? Don't I get the same answer?
Yeah.
Wasn't it worse this way?
Yeah.
So again, I understand you are not familiar with a math teacher saying, hey, sometimes don't use the damn formula. That is so counter to what you're used to because you're getting closer to real life shit. In real life, formulas have to capture everything that could happen. When I'm in a specific situation, sometimes there's a better way. And this way is not the better way. The way you guys did it, 8 of them out of 220, you're done. Done. I don't want to do this shit. Does it work? Yes. Is it the silly way to do it? Yes. This is a silly way. Okay. Maybe? I don't know. Some of you guys were trying, and I really appreciate you trying, but you did not have to do that. All right. So what's up with E? What's the first different thing about E? Different from all the other ones? Given. So what am I given? What do I know about the student? They're computer science majors. How many people am I talking about? 73. Out of those 73 students, how many match what I'm looking for? I'm looking for Grossmont students. 62 out of 73. And then I just put the old calculator. Put an old calculator. Wait, let me see. 0.63. Yeah. What is that? Help me.
0.8494.
I went the wrong way entirely. What am I thinking about? All right, I gotta give myself shit. Hold on. Oh God. Okay, I love it. I did not carry a 2 in my head. That was beautiful, Jeff. So what is it again? I'm sorry.
0.8494.
8494. Sorry. Go ahead. Is it 90? We'll see. Sorry. Do it again. Go ahead. Sorry. Say one more. Say it again. Sorry.
Oh, right there. So for the bottom one, she got 164 instead of the 73.
Oh, okay. If I read this out, find the probability that they're a Grossmont student, given they're a computer science major. So what do I know about them? They're a computer science major. So how many people could I be talking about? 73. So what will the denominator always depend on? The piece that I'm given. Yes? Yes.
Why is it 0.84?
I don't know. I crowdsourced it, so let's see. So it should be 0.8493, yes. Right? 0.8493. All right, now. How you guys doing? Look at part F. We're going to do this one together, obviously, because I haven't talked about the idea of independent. What is the probability that I pick a Grossmont student? We calculated that, didn't we? What is it?
0.745.
Now, if I want to see if 2 events are independent, I want to calculate if one event happening changes the probability of the other one. Let me say that again. If one event happening changes the probability the other one happens, wouldn't you call those dependent events? That probably one would depend on if the other one happened or not. You guys get me? Yes? When you were 2 years old, were you dependent on whoever your caregiver was? So if something happened to them, wouldn't that affect the probability of something you get what you need? You guys with me? Okay, you guys with me?
Okay.
Now, do you care about Fred, who's currently walking down 7th Avenue in Cleveland?
No.
If something happens to Fred, if Fred forgot his wallet, does that change our day? We're independent from them. The probability that something happens to him does not affect the probability something happens to us. You guys with me? The only probability we can calculate that shows how 2 events interact is the given. So, given Fred forgot his wallet, does the probability that we get to class on time change?
Yeah. Oh, not us. Him though. Yeah.
Us. Given that Fred lost his wallet, does the probability that we make it to class on time change?
No.
Hell no. So, if I calculate a given, I see how much one event affects the other one. So I've established what the probability of gross one student is, period. Do we know the probability of gross one student given their computer science major?
Yeah.
What is that?
84.93%.
If I know they're a computer science major, does that affect the probability that they're a Grossmont student? Did the probability change? What was the probability they were a Grossmont student? 74.55%. Did I restart this, dude? Look at me go. Okay. So read with me. Probability Grossmont student is 74.55%. If I tell you they're a computer science major, does that probability change?
Yeah.
Yes, it went up. You guys with me? So in real life, here's a really dumb example that will never leave my head from one of the worst classes I ever took, but this example's okay. If there's a certain kind of soil I see, and the probability there's oil underneath it increases where that soil is, wouldn't I look for that soil before I start to dig for oil? Does that make sense? Do you see what I'm saying? So we use, if it's a certain time of day, might you just stay where you are in San Diego and just wait a little bit before you hit the road?
Right.
So the probability you stay is dependent on what time of day it is. So we use these kind of probabilities all the damn time. Yes? In fact, the very first example I gave you about probability was walking down a certain path to get back to your freaking cave, your tree that you sleep in, and depending on the time of day, saber-tooth tiger's over there, whatever, yes? So you play the probability. This is called I think I already said that it's a conditional probability. On the condition that they're a computer science major or not, the probability of a Grossmont student changes, yes? So these two are dependent. And that makes complete sense. Knowing one changes the probability of the other. So what would have to happen if these were actually independent? What should we have gotten here? I should have gotten the exact same thing I got over there, yes? So if B happens and A doesn't give a shit, so if the probability of, let me write this down. If the probability of A given B is still the same as the probability of A was before, do you see how that tells me A doesn't give a shit that B happened? Fred lost his wallet. None of us know Fred. We're not affected at all. Yes? Now, some of you guys are out there are like, well, there's little ripples, a butterfly, but shut up. I mean directly. We're not affected by Fred and his wallet. Yes? Okay. So this, if I ask you, are A and B independent, you calculate those things. And you see if they're the same. If they're not the same, independent. If they're not the same, then they're dependent. That's it. That's all that means. So which probability is the most important one to calculate when I ask you about independence? The given. Does everybody get that? Okay. So if you don't calculate a given to answer that question, it's never going to be right. That's the one that shows me how they interact. Yeah. Mutually exclusive means, what does exclusive mean? What's the first thing that comes to mind when I say exclusive?
Private, single.
Private, some people can't come in, whatever, yes? And what do you think when I say mutually? Together, yes? So if two things exclude each other, they're mutually exclusive. So for example, if one event was salamander and the other event was pistachio ice cream, is there anything that could be in both groups? Is there anything that is, no, I love you guys are shaking your head, yes. Is there anything that is both pistachio ice cream and a salamander?
Milk.
Does that exist? Is milk a salamander?
Although you said salamander.
Is
ice
there
cream.
anything that is both ice cream, pistachio ice cream, and a salamander? All right, let me give you an example. So those would be mutually exclusive. They exclude each other. Once you are one thing, you cannot be the other.
Can you be mutually exclusive and independent?
No, I love you. You asked the, okay. No, but that gets so, I'm not gonna worry about that. Maybe I'll talk a little bit about that, but that always confuses the shit out of people. What was I gonna say? Shoot. Oh, what about older than 21 and Democrat? Is there anybody that's in both groups?
Yes.
Yes. So are those mutually exclusive groups? No, because you can find one that's in one and the other one. So mutually exclusive, if I tell you that C and D are mutually exclusive events, then I know that the probability of C and D must be 0. The probability, so if I tell you salamanders and pistachio ice cream are mutually exclusive, the probability that I pick up something that is a salamander and is pistachio ice cream is 0. Now, if I have pistachio ice cream sculpted in the shape of a salamander, is that actually a salamander? No, thank you very much. Yes. I'm very concerned. Somebody's gonna bring in the salamander. That is pistachio ice cream, and that's gonna freak me the shit out. It's wobbling around, it's leaving little bits of pistachio ice cream. That's just weird, don't you? I love you guys so much. Yes.
Okay, so going back to Harlem Cat, how do we justify that if they are independent?
So I want you to notice, and I do this all the time, didn't we do all the work we had to already? Probably Grossman is here. Does it change if I'm given their computer science major? Yes. So what is the answer? Are they independent or dependent? They're dependent. The probability they're a Grossman student depends on if they're a computer science major or not. Because the probability they're a Grossman student changed when I knew they were a computer science major.
So did you say that if they are the same, they're equal?
If they're what now? Oh, if these would have come out exactly the same, then they would have been independent.
Oh, and
Because again, if B happens and A doesn't care, they are independent. Yeah. Okay. All right, let's talk about the haunted house. So the first two questions should be really, really simple. Yes? How many people do I have in the house? 21. And what's probably that I pick a Democrat then?
7 out of 21.
7 out of 21, which is 0.3333. Is that cool? What if what's probably I pick a Republican?
12 out of 21.
12 out of 21, which is something.
0.714.
714.
Oh no, 0.5714.
57. All right, so the first two, pick one person, beautiful, yes? Easy, easy, nice. Now I'm gonna pick 2 people with replacement. So me, if I were you, I would automatically put 2 spots down. I got 2 people, they each get a probability, and I'm putting the first person back in, yes? What's probably first person is an independent. So I pick them, they're like, thank you, and then I shove them back in the house. So how many people are in the house?
21.
And how many people are Republicans out of that? 12. So then you just multiply that together and get something.
0.0.
Who is it? 0544?
0.054.
Yeah, it can't be 0.544. It's got to be less than that. 0.0544?
Yes.
Okay, that sounds better. 12 out of 21 is 5714, so about 1/10 of that should be 0.057. Yeah. Is that okay? So when you multiply those together, 2 divided by 21 times 12 divided by 21, yeah, you should get this bad boy. Do you see how there's no and in here, but there really is? I could rephrase this as I pick a Democrat and I pick another Democrat, yes? So I still have my 2. What's probably first one's a Democrat? 7 out of 21. I shoved them back in the house. So I still have 7 out of 21. And that would be 0.11111111. Gotta make up for my earlier wrong answer. I'm still thinking about it. Okay, let me stop for a minute. So if I would have picked 3 people, you would have just had 1 more spot. And if it's with replacement, I just keep shoving them back in the house, yes? On part E, we're gonna be nice people, and the person we pick, we're gonna let them lead. So still got 2 people. Let's probably first one's independent. 200. So these are like the same question, just in a different situation, right? So I pick an independent, then I let them leave. How many people in the house now for the second pick? 20. And how many people are still Republican? 12. So that's one. So that's 0.0571. Yes. I don't trust myself anymore. How we doing? And then 2 Democrats. What's probably first one's a Democrat is of course 7/21. Let them leave. How many people in the house now?
20.
How many Democrats in the house now? 6. And then 1/3, that'd be 10%. Okay. I like it. Okay. So this last one, how are we doing up here? This last one. What's my population I'm working with in number 3? Is that really big?
Yeah.
Yes. How many people am I picking?
3 or
4. I want the first one to think, I don't know if you guys heard about this survey, it's a real survey. Now, if you look into it, it's the way it was worded and so forth, so it doesn't really mean, but it's unfortunate that I'm pretty sure it's a non-zero percentage of people that believe this. But it's not quite so, but it's okay. We're gonna go with this. I want the first person to think chocolate milk comes from brown cows. So what's the probability that would happen? 7%. And then I want the last 3 to not think that. So what is each one of these guys gonna get? 9.3, because I want them to not think that, so it must be the rest, yes? 7% chance they do think it, 93% chance they don't think it. And that would be 8.172, 0.49 roughly, I don't know, 0.5, what is it? 0.562, okay, I forgot to do the decimal. Okay. Let's see. So, if you wanted to calculate this probability directly, the reason it sucks is I have 4 people, correct? And if I say probably at least one of them thinks chocolate milk comes from brown cows, I'd have to calculate all of the following probabilities, you ready? Either the first one thinks that way, and the other ones don't, or the second one thinks that way, or the third one, or the fourth one, or the first 2, because it says at least one, or the last 2, or the middle 2, or the first one, the last one, the first one, the third one, the second and the fourth one, or 3, the first, holy shit. So, since opposite probabilities are always one is 1 minus the other one, any flippin' time, anytime the question asks me something that would take too long and the opposite probability would be quicker, I could just figure out the opposite probability to do 1 minus that. What is the opposite of at least one thinks something? None. The only way you can show me that I'm wrong, if it's that at least one person in here likes season 8 of Game of Thrones, is to show me that nobody liked it. Yes? I think the second thing would be true. Okay? So I want to calculate 1 minus the probability that none of them think that. I want none of the 4 to think chocolate milk comes from brown cows. So what do I want each of them to think then? If I want none of them to think that chocolate milk comes from brown cows,
You wanna think it comes from factory?
we want them to not think that way. So
0.93.
each one is going to get 0.93. So you can do 0.93. You could do to the 4th power, yes. If you want to use a little method magic.
Can I still with time?
Totally, because it's still an and. I want the first one to not think that, and the next one, and the next one, and the next one. So if you do that and then do 1 minus that, you'll get the actual answer. Let's do this. All right. Real quick. All right. I was almost going to let us out earlier. I'm just going to let us out. I'm so tired. The other side, I'm going to have the answer key for this on, what is today? I'm going to have it on Thursday. I'm going to have the answer key to this on Thursday, because when is our double quiz on this? Next Tuesday. You with me? We'll do this last problem next time. There's a little bit of discussion about that. There's a problem in the book I want to show you that goes along with this idea. So I don't want to get into it right now. We're almost done. And I'll have the answer for this one next time. And next time we'll put together the formula sheet officially. Okay. Alright guys. I'll see y'all Thursday. Let me know if you have any questions. Don't forget your stuff, please, dear God. Thanks, man.